Hello, college algebra students. Today we are going to start the chapter 4, and especially today we are going to talk about section 4.1, which deals with exponential functions. So this chapter is about exponential and logarithmic functions. We have seen how do we work with linear functions, polynomials, and rational functions. Today we're going to extend ourselves. We're going to talk about exponential and logarithmic functions, and these functions play a vital role in applications and many applications. For example, we're all talking about coronaviruses these days, right? So here's the number of confirmed cases as of March 25, 2020, number of cases in the world. And if you take a look at the graph, of the number of confirmed cases, as you would see, here is the graph right there. And that graph, represents, if you take a look at the graph more closely, here's the graph, and the kind of graph goes like that. And if you talk to any population biologist, right, they'll tell you that this is an exponential growth, right? I'm sure you heard the term exponential growth, and this is an exponential growth, and that comes from these exponential functions, by the way. So anyway, any graph that's going to have this kind of structure is what we call exponential graph and the way that we represent these functions in generally is that we would write them as y is equal to a constant to the x, and the constants are usual they are positive, right? These are positive constants. So let's take a look at some of the basic important facts about these functions y is equal to b to the x. So the domain for this function is the entire real line, so it's going to go from 0 to infinity, and the range is, as you see from here, the range starts here and goes all the way there, and it doesn't seem it's going to approach the x-axis, so therefore it's going to be 0 to infinity. And the graph passes through the point. If you really see, the graph passes through the point 0, 1 all the time. And if b is greater than 1, if this particular b right here or b right there, if that is greater than 1, the function, as you see when you look at the example of y equals 2 to the x, the function is kind of going like that, right? So that means the function is increasing. And if the b is between 0 and 1, as you see in this particular case, the function kind of, as the x increases, the function kind of goes down and eventually goes to approaching 0, right? So the function is going to be decreasing whenever b is between 0 and 1. The graph has a horizontal asymptote, as I told you earlier. Although it doesn't look very clear in here, the function never touches the x-axis but is always approaching the x-axis. So here the horizontal at y equal to 0, or otherwise you can say x-axis. The y-intercept, where does the function intersects the y-axis, always happens at this particular point. So we can say y-intercept is always 1. And this particular function has an inverse. We'll talk about that in the future sections. Has an inverse function, and so therefore we can say this y equals b to the x function is a one-to-one function. So these are some basic facts about these exponential functions. Let's take a look at how do we graph them. So if you recollect from section 2.5, we talked about how does the transformation work, right? How does the transformation of a function works? We talked about the vertical shift up, horizontal shift up and down, reflection on the x-axis, reflection on the y-axis, and these are the various forms. If you add a plus c to the function, that's a vertical shift up. If you subtract a a c, it's a vertical shift down. If you subtract c with the independent variable, it's a horizontal shift to the right. And then if you add a constant, it's going to the variable inside the function, it's going to be a horizontal shift to the left. And if you have a negative f of x, that's going to be reflection on the x-axis. and if you have f of negative x, that's going to be reflection in the y-axis, right? So that is what we are going to use to graph the following functions. So we are going to graph these functions, but before I graph these functions, let me graph the function. I'm going to say g of x equals 3 to the x, right? Once we graph that, then we can use these transformations to graph 3 to the x minus 1, 3x minus 1, 3 to the x minus 1, and minus 3 to the x, right? We can graph all that. So let's try to quickly graph that. When I plug in x equal to 0, remember this is an exponential graph, right? And this is this value is more than 1, so therefore it's going to be increasing. And when I plug in x equal to 0, that is 3 to the 0, which is going to be 1 right here. And when I plug in x equals 1, you're going to have 3. When I plug in x equals 2, that's 9, so it's going to be right here. So if I graph the function is going to look like this, right? The function is going to kind of look like this, right? All right, now let's see what does this mean. So here is the function g of x equals to 3 to the x. Let's take a look at what is this function is going to look like, right? 3 to the x minus 1. So if you go back in here, this looks like if this is g of x, right? If this is g of x, if I try to find what is g of x minus 1, and you would tell me that would be 3 to the x minus 1. So this function looks like 1 is being subtracted inside the inside the function, in other words with the independent variable. So this kind of looks like this, which is a horizontal shift to the right, right? Which is a horizontal shift to the right. So if I shift this 1 unit to the right, let me copy this graph. Let me paste it, right? So here's the graph. Let me change the color. So here's the graph, right? And that is the graph g of x equals 3 to the x. So 3 to the x minus 1 is basically subtracting 1 from the independent variable. So I have to shift 1 unit to the right. If I do that, ladies and gentlemen, you would agree the graph is going to be looking like this, right? So this would be the graph of 3 to the x minus 1. By the same token, if you take a look at the b, f of x equals 3x to the minus 1, this looks like this particular one, right? This looks like this particular one. So therefore, that's basically vertical shift down. So let me paste it, right? Here is the original graph that we had. And now we are going to shift it down 1 unit. When I do that, then this is going to be this particular one, right here. So let me change the color. Let me go with the blue. So this will be the graph of the function, which is 3 to the x minus 1. Now what about the part c? So if you look at the c is similar to this particular one, which is h of x equals minus f of x, which means that's a reflection along the y-axis. So if I reflect this one, if I reflect this particular green graph along the x-axis, you would agree that I'm going to have the following one: 0, -3, and -9. So the graph is going to look like this, right? And that is the reflection. So let me copy this, or actually let me cut it and then paste it right here. And that will be this graph. So this would be the graph of the function -3 to the x. And this is how we graph these exponential functions. So these are wonderful functions. These plays a very vital role in various applications, and so let's take a look at what are the other applications that we can do. One other application that we can do is compound interest, right? But before we do, I want to quickly talk about this symbol right here that you see. So this is a very special function. There's a very special function, and that is called e to the x. So if you see here, that's the f of x equals e to the x, and this base is the e. This is an irrational number, right? E. It's approximately 2.9 something, or 2.71828, right? So now how do we, if you have a calculator, the way to find the e is the following. So here, if you have this type of calculator, you have to press the shift and the ln. And if you have this kind of calculator, again, you know, press this and then find the press the shift or the second and the ln. That's going to give you e, and then you can work with them. So let's take a quick look at how do we find the approximate values of these using the calculator. Let's try to figure out how do I find this, this, and this. So you're going to use the calculator to do that. When you do that, you're going to have the following values. So if you find the e to the 3.4 into a calculator, you will get this to be 29.9641. When you try to find e to the negative 0.95, you're going to have 0.3867. And if you try to find 5 to the square root of 3, which is 16.2425, right? And again, this plays a vital role in what we call the continuous compounding, and which is useful in figuring out certain growth rate and things like that. So for example, let's try to do one application of this exponential function, the compound formulas, right? So if you're compounding the principal, right, if you're compounding certain investment, and then let's just say the growth is a certain rate, and it gets compounded n times per year for a particular number of years, then how much you would get. For example, let me give you an example. Let's just say you invest $10,000 in the stock market, although and then the stock market gives you 7% growth rate, right? After 5 years, how much money you would have, right? How do you compute those kind of things? So that's where this compound interest, you know, comes into play. So let's see how do we do that. So the amount that you would get after n number of years, after t number of years, is that going to be p times 1 plus r over n to the nt. Here p is the principal, r is the rate of interest or rate of growth, and n is the number of times per year compounding. If it's annual, it's n is 1. If it's semi-annual, n is 2. If it's quarterly, n is 4. If it's monthly, it's 12, and so on, right? And this t is the number of years. You can also do the compounding continuously, and that would be, the formula for that would be p equals a equals p times e to the rt, where p is the principal, e is the exponential function, that e 2.7 something, right? We talked about 2.7182, remember, 7.828, and then r times t. R is the rate of interest, and t is the times the number of years. So let's try to do this example. So how do we do this particular problem? So somebody is investing, right? Somebody is invested about $6,000. And the question is, so you have three scenarios. Scenario one is if they're investing for about 4 years, how much the person would have after 4 years if it's if the interest rate or the growth rate is 8.25% compounded quarterly, 8.3% more, actually the growth rate is higher, the interest rate is higher, but it's compounded semi-annually. Now sorry, the growth rate is higher but compounded semi-annually, In this case, if you look at the third case, which is 8.2% compounded continuously, so you have a lower growth rate but then compounded continuously. So let's see how much, let's try to compute how much these persons are going to get. And by the way, these are the similar formulas used for calculating your mortgages, calculating various other things, right? So if you want to get into real estate, you must know these kind of formulas. All right. Or any finance, any real estate, anything that deals with the money, or stock market, analyst and things like that, you should know these formulas very well. So let's take a look at this problem. So let's take a look at this case, namely 8.25% compounded quarterly, right? Let's try to write down the variables. So the investment is 6,000, so that is going to be my P. P is 6,000, right? And the investment is for 4 years, so the T is going to be 4 years. In this particular case, the growth rate or the interest rate is 8.25%, which you can write it as 0.0825. And since it's compounded quarterly, that means that number of times they compound is 4 times in a year, so n is equal to 4. So if I plug all these information into my formula that I have, right, you would agree that I'm going to have A equals 6,000 times 1 plus 0.0825 divided by as you see, it's 4, right, because n is 4, times n is 4, time is also, the number of years is also 4. So if you do that, if you use your calculator, they should give you something around 8317.84. So it's kind of an approximate, it's not exactly, it's going to give you some sort of an approximate value there. Right, so if a person is investing $6,000 for 4 years, if the growth rate or the interest rate is 8.25% and compounded quarterly, the person will have $2,317.84 more than what he or she has invested. Let's take a look at the second part. The second part is very similar, except that the growth rate is higher. So the P is the same, T is the same, the R is going to be different and N is going to be different. So in this case, P equals, so again this is 8.3% compounded semi-annually, right? So P is still 6,000, T is still 4, and R is now, it's higher, which you can say 0.083, and N is now lower because they are doing semi-annual, so N is going to be equal to 2. Again, if you plug this into the formula, A is going to be 6,000 times 1 plus 0.083 divided by 2 times NT, N is 2 times T is 4. So then this would give you, if you use your calculator, this should give you 8306.64. So I want you to quickly observe one thing in here. Although the rate here is lower, since it's compounded quarterly, you see you have more money here. The rate is higher, but compounded semi-annually gives you much, not less, it gives you less, right? So if you're investing for a long time, that can become significantly higher. So the compounding is more important, right? Of course, the growth rate is also important. Let's take a look at the compounding continuously. So what would that be? So if you look at the part C, so now we're looking at this particular part, right? 8.2 percentage. It's a lower rate but compounded continuously. So 8.2 percentage compounded continuously. When we do that, what happens? Still the investment is P is 6,000. Still no, here is not. So that's the only thing I need here. I'm sorry. So R is equal to 8.2 percentage, which is 0.082, and time is 4 years. There is no n. Actually, technically speaking, n here is infinity, by the way. So if I plug this into the formula, ladies and gentlemen, the formula is A amount that you will have after t years would be P times e to the RT, where e is the irrational number, which would be 6,000 times e to the 0.082 times 4. And when you do that, you will have approximately 8329.13. So if you see here, this is still higher in both the cases, right? So you have a lower rate, but because of the continuous compounding, you still have the higher value. And that's how we would make use of these particular functions, right? Exponential functions. And this is one of the applications. We'll talk about the logarithmic functions. These are basically inverse of exponential functions. So we'll talk about them in the next section. I'll stop it right here. Thank you very much.